This video is to help you understand Gershgorin's theorem. I'm going to presume you've already looked at exploration 1 and you've changed some of the entries of this 3x3 matrix and seen what it does to the circles and tried to answer some of the questions. So we're going to begin by helping you understand the statement of Gershgorin's theorem. The conclusion of the theorem is that the eigenvalues of A are contained in the Gershgorin region gamma of A. That's a capital gamma, which is the Greek G. And it's defined in the equation right above it. It says that gamma of A is defined to be the union of the gamma I of A's. Now these gamma I's are Gershgorin disks. And it says the union as I ranges from 1 to n. So there are going to be n disks if you have an n by n matrix. So in the exploration, you had a 3x3 matrix, and you saw 3 disks. And the eigenvalues always appear in those disks. I guess the only other thing is this equation 1 here. What is this? This says how to define the ith disk, right? So if I wanted the second disk, gamma 2 of A, well, it says it's the set of complex numbers, z in the complex numbers, such that, and now it says the absolute value of z minus A22 is less than or equal to R2 of A. All right, and I'll explain what that is. But basically, this is the equation of a circle in the complex numbers, or actually a disk. Equal to would be circle to a circle. Less than or equal to this radius is the whole disk, the circle and what's within. So A22, that's a diagonal entry. That's row 2, column 2. So see, these are AII. And so I guess the centers of the disks are the diagonal entries. And we'll see this in example 1 in just a second. Now, what about the radii of the disks? The radii are these absolute deleted row sums. So what is R2 of A? R2 of A is a sum. It's a sum of certain entries. These entries would be A row 2, because I is 2, and then whatever J is. Now J can be anything except I. So basically, R2 of A would be A row 2, column 1 plus A row 2, column 3, except that you want to take the absolute values of those things. And so we'll see how this all works now in this next example. So it asks me to plot the eigenvalues and the Gershgorin region of each of the following matrices. I'll start with matrix A. And so we're going to plot gamma 1 of A in blue. And so if I look at row 1, well, this 1 right here, that's the center. And so there is a center of the disk at 1. And the radius of the first disk is also 1. And so my Gershgorin disk is a circle of radius 1 centered at 1. That's not too hard. Let me get a different color for gamma 2. Why don't we use red? And so for gamma 2 of A, well, again, it's the diagonal entry. So that's the center of the second circle. And so it'd be centered at 0, which is right there. Remember that these are complex numbers. So example B will show that a little bit. And the radius is the absolute value of everything else. So there's a 2. So we want a circle of radius 2 around 0. And so I guess it would look something like this. Okay. Now I didn't compute the eigenvalues yet of this matrix, although it's pretty easy to do, right? So if I wanted to take the characteristic polynomial, I would take the determinant of the matrix 1 minus lambda, 1, 2, and 0 minus lambda, right? Because this is going to give me the characteristic polynomial. Negative lambda times that gives me lambda squared minus lambda, and then I need to subtract the 2. And so this factors pretty nicely. It's lambda minus 2 times lambda plus 1. And so that tells me that the eigenvalues, which I haven't plotted yet, but I'm supposed to, are positive 2 and negative 1. And notice positive 2 is right here on the boundary of the two disks, and negative 1 is in the red disk. What the theorem says is that the two eigenvalues will be in the union of these disks. In this case, the blue disk is totally inside the red disk. So basically what I know from the theorem is that the eigenvalues have to be somewhere in this red disk. And it turns out that this is where they are. So for part B, matrix B, let's plot the eigenvalues first. We're lucky to have an upper triangular matrix because then the eigenvalues are the diagonal entries. So 1 plus I, well, that would be 1 on the real and 1 in the imaginary, so it's this point right here. That's the point 1 plus I. 4 is also an eigenvalue, so here's 4. 2 is also an eigenvalue, so here's 2. And negative 1 is also an eigenvalue. So those are the 4 eigenvalues. And it turns out that those are actually the 4 centers of my circles, because remember, Gershgorin's theorem says that the centers of the circles z minus aii, right? And so a11, a22, a33, and a44 are the centers of the circles. And these are less than or equal to ri of a, the radius you get from the absolute deleted row sum. Okay, so my first circle, so what does that look like? Gamma 1 of a. Well, that's a circle, and it's centered, as we said, at 1 plus I. And the radius, what we need to do is we need to take the absolute value of the other entries added up. So this radius is going to be 1 plus the absolute value of I. The absolute value of 1 is 1, plus the absolute value of 0, right? But that's just 0, and that's 1. So the absolute value of I, what's that? Well, that's 1. Why is that? Because remember that absolute value measures how far away something is from 0. And I is 1 away from 0. So I guess the radius here is 1 plus 1, which is 2. So my first Gershgorin disk, centered at 1 plus I, right, here's 1 plus I, has a radius of 2. And so I can draw it. Looks like this approximately. And that's the first Gershgorin disk. Okay, the second disk, let's switch to, say, red. And so it's centered at 4. And its radius is 0 plus the absolute value of 1 plus I. So what's the absolute value of 1 plus I? Well, that's how far 1 plus I is from 0. There is another way to compute the absolute value of a complex number z. And what it is, it's the square root of z times z bar, where bar means complex conjugate. And so I guess in this case, what is the complex conjugate of 1 plus I? It just means switch the sign of the imaginary part, so it's 1 minus I. And so if you work this out, you get 1 times 1 is 1, negative I and positive I cancel, minus I squared. Of course, I squared is negative 1, so what we really get is the square root of 1 plus 1, which is the square root of 2. And you probably knew that that radius, that distance from 1 plus I to 0 is the square root of 2. You could do that with geometry also. So the square root of 2 is about 1.4, and so my second Gershgorin disk looks something like this. It's a radius of just over 1.4, the square root of 2. Okay, How about the third disk? This is going to be a little easier. What's the center of the third disk? Well, again, it's A33, so it's 2. Let me get a blue pen for this one. So gamma 3 of A, well, the center is 2. What's the radius? The radius is the absolute value of -1, which is 1. And so the third disk is this. And so that does give us a little bit more of a region. Okay. Now the fourth Gershgorin disk, it's centered at -1, but it actually has no radius, right? The radius is 0. And so the fourth disk is just that point there at -1. And so this is something else that can also happen. But the Gershgorin region would be these 3 disks in that point. And all the eigenvalues must be contained in that region. So I hope that this has helped you understand Gershgorin's theorem, how it works, and can help you complete the rest of the section.